This is now the sixth module of the short ROS course here at HUI on December 1st. The module is the second part of Gazebo ROS integration, and most of the students in the class have just finished the previous module. Some are still working on previous modules. That's okay. I urge you, if you're as you work through them, take your time to finish each module completely and make sure that you feel you've mastered it before you actually do the work on the next module. You can certainly read about the next module, but make sure you master the previous module, because if you got that down solidly, then it makes things easier going forward. The goals of this, we saw in the last module that you can add additional parameters to your Zacro file or an RDF file, and then it will be a fully qualified, it can either generate or will be a fully qualified SDF file, which is what Gazebo needs in order to do simulations. And it became completely obvious as you worked with them why it makes sense to keep one source file describing the robot rather than trying to push different versions. And then you experimented a little bit with loading that robot model into Gazebo, and you loaded a world into Gazebo, and so figuring out the mechanics of that. Once you figure out the design pattern of where you expect things to be, then it's pretty easy to deal with. There are idiosyncrasies. We discovered a number of idiosyncrasies. Several sort of issues with slight changes in spelling in names of joints and links and things like that came up on sort of several different cases. What are other sort of snafus that people encountered that confounded them?
I moved when I was making my model, I moved the origin to the wheels to get them on the robot instead of the origin of the joints.
Since the origin of the joints, right?
Yes, that's screening over the
Yeah, and that was where your robot was falling into the ground, right?
It was doing something bad,
Yeah, and it wasn't the collision. The Gazebo uses the collision objects in order to simulate contact between the objects, and it simulates contact with a very high default. You can set the other parameters. It uses a PD contact model, proportional derivative, so the force of contact is proportional to the depth of intersection and the velocity of intersection, and the default is a fairly high stiff value, probably that equivalent to like UHMW or some fairly dense plastic, not steel, and it's got an artificially high damping coefficient for the impact in order to damp things out, so things don't just ping pong around forever. Any other snafus that anybody wants to share? I've done all of them over the years.
I never did figure out why, but with the PR2, I started driving around with the wheel forces, and then I set them back to 0 and kept driving.
With the PR2 or with your?
Or with the Pioneer.
With the Pioneer.
Yeah.
Oh, probably because there's no friction in the model.
Oh. Okay.
And so it's gonna persist. So if you don't put any, like in the joints of my edge emip, I put friction in the joints. I added a friction parameter in the joints, so I want it to damp out eventually. But this is a physics model, and so if the damping associated with contact force actually uses no energy because it's rolling contact. Rolling contact is effortless, and the physics model represents it as such. And so unless you have some sort of a friction in your model, it's just going to ring forever. It's going to go on forever. The one that I had driving around for the last 4 hours in Gazebo, I just was driving it and I used black tape as a stick lock. And so I wanted to show that you actually can run Gazebo for more than once it crashes when you start, but once it's up, it's reasonably stable. Any other snafus to share? All right, so I'll do just a brief overview of this afternoon's goal, and I really already demonstrated the idea. The thing you're going to do is run your Gazebo program almost exactly the same way you did before, but we're going to modify the SDF to add some new features to the Gazebo simulation. And to remind you, I showed you this at the beginning of the last module, but I'll just bring it up again. So we've got a simulation here of a robot and RQT graph. And right now, ROS core just knows about one node, Gazebo. And then I'm going to ask you to make, you already made a launch file for Gazebo ROS with launching your robot so that it appears. And then you found that if you applied torque to the joints, then the thing would drive around. It's interesting, on my display I can't actually see it, but right here there's a little sort of marker that you can see, a couple of dots, 4 or 5 dots that you can see on some displays, but they seem to have done something wonky with the contrast because I can't actually see it, but I can drag on that tab. And if you drag in just the right spot, go over and look at Carl's machine. You can see them very clearly at Carl's machine, but on our 2 machines you couldn't see them at all for dragging this out, but it's a left button drag. And of course you only get access to those joints when you've highlighted the whole robot. And I hope you experimented with things like gravity and made the robot fly off into the universe and things like that. We're going to connect Gazebo to RViz, and you're going to ask you to generate another launch file, which is edumyRobot RViz.launch, and I'll show you my examples. And so there's RViz. You might want to pull those curtains a little bit. I don't know if you guys can see that at all. And we could around the robot. So how is this done? As follows. Node, publishing a joy twist, publishing by a plug differential drive controller. We're sort of faking. It actually does the balancing as an active a pendulum under the robot, and differential drive controller plug node that you can use on your real. And they expect to give velocity commands to 2 wheels. What they normally do is they'll normally publish, and they will also a few other things that they and right in this 5-line hello world, so that it just that are published by and this block, which we cannot the differential controller is it's publishing joint states, and cleaner simulation if we with Gazebo. As you can see that link states parameter description. Then ROS and you can fiddle with when you bring up an image by and introspect into other, usually like one. SDF. ROS. So this talks about basically the syntax of what a plugin is. It goes right in your SDF inline, and this gives an example of what the syntax minus the detail of the parameters looks for a differential drive controller. And the differential drive controller has a plugin name, and it references a particular C compiled object over here, which is going to be loaded on the fly. And bless you. And more details about plugins. And the RR bot is an example that they give, where they give a full Zacro file, which specifies a revolute robot arm. So it's an robot arm that's standing vertically with two horizontal rotational joints. And they're not showing the whole Zacro file. They're just showing that there's a joint and there's a camera that's being attached to that. And the camera has a visual expression, and it's got some size, and it's got an inertial expression. And then so there's a camera link, and then on the camera link, attached to the camera link, is an actual camera. And this is what the camera plugin code looks like. It specifies the update rate, the field of view, all of the camera physical parameters, including noise, sensitivities, range of vision, and things like that. And this tutorial walks you through the different parameters and discusses what they are. And this is what the simulation looks like. In this simulation, the robot is uncontrolled, and so it starts with the links pointed to the sky, and it ends with them dangling down. You can skip multi-camera for now, and you can skip depth camera for now, but suffice it to say that there's simulators for that. The RR bot, this robot is called the RR bot. It's not mobile, it's a fixed joint. It also has a laser scanner attached to it, and there's a plugin for that. And so they had attached a joint called Hokuyo joint. Hokuyo is a major manufacturer of laser scanners, so you can buy super nice laser scanners that are about this big for $5,000 that give you 100-meter range and full daylight capable and do 50 scans a second. They're pretty amazing pieces of equipment. And so the Hokuyo laser is attached to the robot by a fixed joint, and And then here's the Hukuyu laser plugin, which says that it's a GPU ray sensor. And I'm going to have to check this because on machines that do not have discrete graphics, the last time I did this demo, you had to change GPU ray sensor type to ray sensor type. So it wasn't looking for a GPU in order to compute the ray tracing. And so if you have problems getting your laser scanner simulation to generate a laser scan, then let's take a look at that. And the other thing, there's a tag for visualize here that's in the Gazebo file, and by default it's set to false, and that's whether you visualize the laser scan in Gazebo. And I'll show you an example of that. So to run this, you need to run 2 launch files. We're going to run Gazebo, and then we're going to run RViz. And what we'll see is 2 different things when everything's turned on. We'll see the robot arm here, it falls down and dangles, and if you drop some objects on the plane here, and you turn this laser visible to true right here in the Zacro file, then it gives a representation of the laser with a maximum range and a minimum range, and where the laser hits things, there's no laser shadow behind. And that's being published on a scan topic, which is it's like RBot laser / scan is the topic name, something like that. And this is RViz's representation of the RBot. Notice that this thing is still standing up, and that's because at this point in this demonstration, the joint states of the simulation haven't been connected to the joint states of the RViz, so don't let that bother you. It's just not correct. And when you first bring this up, when this is publishing laser scans, oftentimes you can't see, this is the scan line here, you can't actually see it, and so if you increase the marker size from 1 centimeter to like half a meter or a meter, then they become really big and easy to see. And you increase the marker size over here in the yeah, there's a little. They actually updated this didn't used to be part of the tutorial. You had to figure it out on your own. So if you have a non-GPU machine, you may need to change this in the Zacro. So let's just run that. This is all the tutorial. So I'm going to ROS launch in the package r.gazebo, which you loaded already in the previous into your workspace, and we can look at it. And so you see it's in my ROS Catkin workspace. And notice that that r.gazebo is a package that lives within Gazebo ROS demos. So you get cloned Gazebo ROS demos in the last module, in module number 5, and this is a project which consists of actually 1, 2, 3, 4. It's a Git repo which consists of actually 4 projects that are related to each other. And so this is an example of a hierarchical project where you pull down one directory tree into the source directory of your workspace, and you get 4 different projects underneath it. And Catkin Make deals with that just fine. So r.gazebo doesn't have any code in it. What it has is worlds files, so ls worlds. It's got a r.world, and it's got a launch file. And so this is the world file, which basically specifies a ground plane, sun, and a little bit about the focus of the camera and the tall pendulum. And if we look at the world file launch, r.world.launch, you can see what goes on here. There's a whole bunch of little parameters that are set to false or true. And this design pattern is one that you'll see in packages. So, for example, if you want to do AR tag tracking and you use the AR track alvar ROS package, which is a very common and popular package for tracking AR tags, and if you track the AR tags with a depth camera like a Kinect, it'll give you a 6 degree of freedom pose estimation for the tag. It's pretty impressive. If I have time this afternoon, I've got an R200 in my backpack, and if I have time, I'll fire that up so we can track some AR tags. It just depends on how busy I get. So in these big open source packages, oftentimes you'll have a couple of pages of parameters and complicated things, and they give you default parameters that should kind of work. For example, if you use the Gmapping package, there's a full page of parameters for tweaking the parameters of Gmapping, and they give you suggested values that they think might, default values that they think might work, but you'll often have to tweak them. So this is just setting up some, this is giving some default values. Here we're loading empty world.launch, and we're setting some arguments for empty world.launch. You can see that it's loading r.gazebo worlds r.world using the find command, and it's going to load the r.zacro from the package r.description, so a different package than this, a little confusing. And then it's in order, which is a historical anachronism, and then it's going to pipe it through macro so that the thing that appears as a parameter in robot description is an rdef because it's been filtered by Zacro. And this is the same syntax for spawning a model within Gazebo, and Gazebo is launched up here. This is commented out, so we can ignore it. And let me think. I want to go to ROS CD rbot description. So this is where we are. We're in Gazebo ROS demos rbot description, and we want to take a look at the rdef directory. And the rdef directory is a little more complicated here. It has the main file is r.zacro, and as we'll see, r.gazebo and materials.zacro get included in that. And this is not an uncommon design pattern to ghettoize the things that are Gazebo specific into a Gazebo file, and group material properties into a file, because that way you can copy it to other things. And this is sort of a typo. r.xml is actually an rdef, and so it is an XML file, but it would be less confusing in this example if r.xml was called r.rdef, because that's what it really is. It's the output. And so if we look at, let's start with r.zacro. And if you're having trouble seeing this, don't hesitate to pull up curtains more. So r.zacro, it's a Revolut manipulator. This is the standard mantra for using Zacro. You include this, and it makes this a Zacro file. Define a bunch of parameters that we're going to use for things, pi, mass, width. And we're going to import the file r.gazebo, and we're going to import the file materials.zacro right here. So we're going to import r.gazebo, And these are the Gazebo specific things. And you can take some time. You can see the RViz doesn't care about things like friction. And so this is defining Coulomb and viscous friction for different links. This is defining the Hokuyu laser, and if you need to change the type from GPU array to GPU, you do that in this file, r.gazebo. These are the parameters of the laser, noise. This is the plugin for the camera parameters. And notice that in both cases, if you switch from the type GPU ray to GPU no ray, you need to change this right here. And down here, you need to change the name of the plugin. This is the name of the plugin, and the actual executable file is this .so. And you'll need to delete underbar GPU because there's two executables, one that uses the GPU on your computer and the one that doesn't use the GPU. This is the plugin for the camera, and like all plugins, it has a canonical name, and it has a name that you specify because you might have more than one instance of this on your robot. You might have 10 cameras. They're each going to have a unique name, but they're all probably going to be using the same executable, and that's okay. And these are dynamically loaded into Gazebo on the fly, so that you don't have to recompile anything. There's a million parameters in these things, even for something as simple as a camera. But cameras really do have these parameters, so physics matters. And then materials.zacro. Material name is black. That would be color in my world, but and remember that the color specification is red, green, blue, and alpha, or opacity. So that's the material file. And then back to the Zacro file. So we began a robot, and a robot consists of a collection of links and joints. And problems that some of the problems that people had were and this is new. We haven't seen this before. Here's defining a link, and the name is world, and that's it. There's a link whose name is world, and in RViz the fixed frame is going to be called world, and so it's going to plunk this robot at the origin. Because the RViz fixed frame is by default at the center, and the fixed frame of this robot is going to be the same name. So unlike our movable robot, where we had a transformation from world to base where we published it and moved it around, this is going to be a fixed transformation. And there's going to be a joint, which is of type fix, which is a joint, the parent is world and the child is link 1. And so that's the static transformation. In these 5 lines, it's easy to miss them, but there's actually a bit going on here that's different than we've done before. And so we're not going to have to publish the relationship between the world frame and link 1, which is the first link. Should be link 0. We're C programmers. Should be link 0. And so the base link, the most proximal link, is link 1. It's got collision geometry, a visual geometry, and several folks experienced that if you take the origin expression and you move it inside the geometry expression, then it gets completely ignored, and you get unexpected results. So the syntax for this XML file is origin needs to come before geometry in both the collision and the visual. The order that these appear, these like inertia, visual, and collision appear, is completely irrelevant. It doesn't matter. And so there's a little bit of math going on here. I think everybody figured out how to do math with Zacro parameters, so you put the math inside the curly brackets. And then here we're specifying a joint between link 1 and link 2. And you define an axis, so the axis is along the y direction of the link. And you specify the origin of the axis, parent and child. And this is where we're specifying damping. If we this arm in the simulation in Gazebo begins up here, and it kind of falls down because a little bit of numerical noise makes it fall off the unstable equilibrium. And so if we dial these dampings down to 0, then it's going to ring forever. It's never going to damp down because it's a conservative system. So there's a middle link, another joint with some inertia, a joint between link 2 and link 3, and there's link 3. So this is just more of the same. And then on link 3, there's a fixed joint. You could put the Hokuyu laser directly on link 3. The authors here have chose to make another, a fixed joint, and that just allows them to move the Hokuyu laser away from the origin of the link in a graceful fashion. So you can place the Hokuyu sensor somewhere on the link that's not the origin. And so this is a fixed joint between link 3 and the Hokuyu link. And the Hokuyu link is defined here. It's just a little box. See, it's a tiny little box. And it's got a visual representation here. And so this will load up a mesh for the Hokuyu sensor. It's got some inertial parameters. And then there's a joint from link 3 to the camera link, which is also allows you to place the camera on link 3 in a place of your choosing. This is where it's placed. This defines the camera link, the joint between the two. And then here we're getting into some more details. This is related to ROS control. Gazebo can distinguish between joints and motors, so there might be a gearbox. Gazebo can accommodate a linear relationship between joints and motors, and in general that's something that happens in robots. The torque on the joints is linear. Torque on joints is equal to an allocation matrix times motor torques, and those depend on the gear ratios of the motors, number one, and number two, if there's coupling between the joints, then that's, for example, if sometimes the motion of joint 1 and joint 2 are coupled because of some chain drives and things like that. Gazebo is able to take care of that. In any robot that you're likely to see, simple robots, especially for simulations, there's going to be one motor at one joint, and you can set the gear ratio to be 1. So this is kind of a distraction. We saw in the previous file that we looked at, RDIF, it was RRBot, Gazebo. These are the things that are unique to Gazebo, and we saw that. So how do these plugins get associated with the robot? They get associated by name because in the robot there was a link created called a Hokuyu link, which was placed at the right spot where we wanted the Hokuyu sensor. And so this plugin doesn't appear in line as part of the Hokuyu link. It's in line as part of the robot because it's been included before the beginning and end of the robot statement. So it's there in the robot, but it's associated with the Hokuyu link by name right here. And same thing for the camera. And to get back to the Zacro file, so we have beginning of robot statement, end of robot statement down at the end of the file, and the robot Gazebo is included here. It names the link that those sensors are placed on, and those links are defined further down the file. The ordering doesn't matter. It'll all sort itself out. All right, so Gazebo packages the ROS. So Gazebo plugins with ROS, we just looked at that one. ROS control, don't spend too much time on this. this just gives you sort of an overview of the ROS control package, which is kind of a crappy package for doing joint control. I wouldn't recommend spending too much time on it. It solves some problems that aren't, in my opinion, problems that hold us back a whole lot. So you can read this, but don't spend a huge amount of time on it. This example uses ROS control. If you follow through in all the tutorials, you'll eventually be able to exert control on the robot and send set points to the robot and make it move around. And so I wouldn't spend a huge amount of time on this. This focuses in on these transmissions and joint efforts and things like that. And then this package on ROS control, I'd say that you could do it or skip it if you're in the interest of time today. Probably a good exercise to do it in the fullness of time. And what it'll do is this is asking you to set up a package where you're firing up some ROS control nodes, some standard ROS position controllers, and those position controllers, you give them the names of the joints, and you give them set points and PID parameters, and they'll do closed loop control. And so the way that works is here in this launch file. So if you fire up a copy of the, you load up some ROS control parameters. You spawn some robot controllers for the 3 joints, and then you do some other mumbo jumbo, and then you can do closed loop control on the robot. And this gives you an example. You have to do some service call to initialize the controllers for the joints and for the 2 joints, and start the controllers, and then you can set points to the controllers, and so you can move the arms around in an incredibly crude fashion. In the interest of time, if you want to skip over this, this also shows you how to use how to generate you can generate time-varying reference trajectories, and you can watch the robot respond to it. And you can use RQT plot, which is kind of a crappy utility to plot it. And this is our first look at dynamic reconfigure. We're not going to cover dynamic reconfigure in this short course, but I'll just mention it now. You're all familiar with the notion that when you design some sort of software that interacts with things, you often want to fiddle with parameters, and so what you end up doing is you end up running the program, setting parameters in an initialization file, running the program, seeing how it works, killing it, changing a parameter, running the program, repeat ad nauseum until you sort of figure out what works properly. So dynamic reconfigure is a utility that you basically set up a configuration file that defines a service, that the service has a call where that your program is going to provide your service. Your program is going to be the service provider, and when somebody makes a call to that service, they send to your program a complete set of parameters for the program, and the service responds back with what it did and possibly other information. And you, in the dynamic reconfigure file, you just tell it what you want the parameters to be: their their strings, their 1 through 5, they're a double precision number, and what the ranges are and what the default values are. And it'll give you these little sliders when you run it. It'll generate the message files for you, and it'll also generate a graphical user interface for the widget to vary the parameters. And when you vary these parameters, it'll send off service calls to your program, and then you'll get a response which will update as to what the program is actually doing. And so dynamic reconfigure is a nice utility and there's a nice tutorial on it. So for sort of tuning systems, it's a nice interactive utility. You just tell it what the parameters are, and then it automatically generates a service definition for you. And all you need to do after that is respond to the service, make a service, provide that service in your code, and it does all the GUI stuff and message generation. So it's kind of nice. And so ROS control, ROS communication with Gazebo. Bless you. So this example is kind of fun because you're going to spawn a model in the in Gazebo. So bless you. So here's our robot arm that's pointing up in the gravitational field, and it's going to start falling down pretty soon. And so this is, we're going to spawn a model of, so we're going to do ROS run Gazebo from the command line, spawn model. So this is the package. Spawn model is the program. And we're going to pull the model of a Coke can from the database. Y1, I don't remember what Y1 is, I'll have to look that up. And so when we spawn the model, voila, Coke can appears. Sorry. Coke can disappeared here. And then we can interrupt with physics, and so we can reposition the Coke can. And this command, sorry. So this command says ROS topic pub minus R20. So it's going to publish at 20 hertz. It's going to set the Gazebo model state. So it's going to set the parameter Gazebo model state with a message of type Gazebo message model state. And here's the contents of the message. The model name is Coke can, and it's going to set the pose and the position and velocity of the Coke can to be up off the ground. And so when we do that, we can levitate the Coke can or let it fall by hit Control C. So minus R 0.2 0.5 maybe. Oh, how about R1? Minus R1. So we'll reposition it once a second, and from the command line. So we're interacting between ROS and Gazebo, and the model will make this guy, database will make this guy Coke can 2. And so there's Coke can 2. And so Coke can 1 minus repeat 0.5. So every 2 seconds we're going to pick up the Coke can and drop it, and I take that same command and we can start picking up Coke can 2, and they interact with each other when they bonk onto each other. So you can see that it's actually simulating contact physics, and you can also see that the contact is fairly dissipative. So the coefficient of restitution is fairly high, but the contact is fairly dissipative. If you turn down the dissipation, and these things bounce around like crazy Mexican jumping beans, because they never lose any energy when they make contact. And it's the derivative term in the contact model. So there's a Kp proportional, that's lossless. It's the Kd term, the derivative term that's proportional to velocity, that's the lossy term for the contact model. you get the idea. So this is ODE, which is what's behind here, is not an amazingly high fidelity physics engine, and detecting contact physics and modeling it is really an open problem if you want to do it at a high level of fidelity. But in my experience, a moderate level of fidelity, which is what you have here, can buy you a lot. You can sort of do a lot with it. Services to create and destroy models. This is all in the subject of interacting. So you can interact via ROS topics with Gazebo and control it. And we saw some examples. And I think you can skim over most of this stuff. Force control. You can apply forces to these in the simulation, in the Gazebo simulation. Over here, we could select the robot if we wanted, and we can apply forces to these things. So 5 newtons, 10 newtons, 20 newtons, 0 newtons, and one of these is going to hit the Coke can soon, I hope. Okay. Back to the main event. So ROS control, ROS communication with Gazebo, ROS plugins. This is the example that gives you a little tutorial that gives you you write the Hello World plugin, and here it is. Basically, it loads up and it prints Hello World. And the way plugins work is plugins are a bit of C code that you compile, and they get loaded dynamically. And they have access through they're loaded dynamically, and they become part of a class. And the class has member functions that lets you access a fair amount of the state of the simulation is exposed to you. And so you can query the states of all links, positions, velocities, things like that, relative positions. And so a lot of the things that you're used to doing in the ROS world, you can do over here in Gazebo with the internal workings of the simulation. So a good deal of the state of the simulation is exposed to you. Not all of the low-level details of the simulation are exposed to you. The actual numerical integration. You can have your plugin called at every step in time, at every integration step in time, if you need that level of granularity. And so this gives you a cookbook for how to make a plugin that will basically print Hello World, but it's the template for how you do it. And were you to do something more sophisticated in here, so if you wanted to simulate some sort of a sensor, then, for example, if you wanted to simulate a depth sensor, you might query the state of the frame, the pose of a particular frame in the simulation, and the z dimension of the origin of that frame is the depth of your depth sensor. And then maybe you'd run that through the inverse of the Fafanoff formula to compute what the pressure would be, and then you'd publish the pressure. Is sort of talk through an example of how you might simulate a simple sensor. And then advanced ROS integration is the last tutorial. Advanced is maybe a little bit of a misnomer. Oh yeah, this is the little tutorial on dynamic reconfigure. If you have time, do the tutorial on dynamic reconfigure because it's just nice. In this example, they run a dynamic reconfigure that lets you give sliders on gravity, and so you can have godlike authority over levitating robots in the simulation by sliders. So dynamic reconfigure is worth your time. It'll take you like 15 minutes to master it. All right, and so the exercise, I'm over my time. The exercise for today is to set up a system that works like this. Your robot is going to be running in here. You've already know how to load the SDF in here. I'd like you to add a couple of plugins, a camera plugin, so that you can see, so that you add an extra camera link and a camera plugin, and then add a differential drive controller to the simulation, And you'll see that the differential drive controller publishes the TF of the base, the published joint space. It also publishes this odometry message. So in RViz, you can add an odometry marker type and set the topic that it's listening to as edumip odom, and it'll generate those little odometry arrows. And so I've given sort of a fairly detailed set of instructions. I haven't given you the exact source code to plug in to cut and paste, but the ones where I thought that you'd spend a lot of time flailing without actually learning much would be there's a whole bunch of parameters here in the differential drive controller, and in the documentation they just tell you what the parameters are and they don't tell you what reasonable values are. And so this is the set of reasonable values that I used in my plugin, and you can see how this plugin works. The command topic is edumip command. That's the command that the differential drive controller is going to receive a twist. It's going to publish its odometry topic here. This is really confusing, and you can read the documentation on this and you can tell me whether it makes any sense, because it didn't make any sense to me. So the odometry frame is actually the fixed frame, and the robot base frame is the edumip body. So this is the differential drive controller is going to publish a frame, which is the frame between world and edumip body, and I don't know why they call this the odometry frame. Publish TF, yes, you want to publish TF. Publish wheel TFs, that's up to you whether you want to publish TFs for the wheel. We really don't need to, because we're going to be publishing TFs anyways within RViz with the robot state publisher. Publish wheel joint state, yes. So it's going to publish the joint state message for you. You don't have to do that. And odometry sources world. I think that's it. And as usual, you give a name for what this plugin, that's the name of the instance, and this is the actual executable that it's going to use. And these are the parameters that I used for a plugin, for a camera plugin. And I already ran this, and you can see the camera. In RViz, you can see the markers and the markers here, and this is what the view of the camera from the robot. So it's fairly detailed instructions, and so take a look at them, and I'm gonna, no, that's okay. Yeah, I think that's it. So my robot Gazebo ROS RDF, and so my RDF here has all the stuff that you've already done. You've already added things, and in addition down here it'll have a camera joint and a camera link added to it, and then a camera plug-in, and this is where I plugged in my differential drive controller, and that's it. So it's really not that hard. And my launch file, there's two of them, one for Gazebo we've already seen, and one for RViz that's here. And what I need for RViz, and this is described in the text of the assignment, is I need to load the robot description, and you already know how to do that. You've done that before. We're going to run a robot state publisher, which is going to it's going to subscribe to the joint state message published by the differential drive plugin, and it's going to publish the TFs of the two wheels. And you need a joystick to drive things around, and then you need to fire up a copy of RViz with an initialization file that you create and you store in the RViz subdirectory of your package. Any questions? All right, let's go to it.